So we were discussing stability, and there was the argument that, okay, there could be algorithms which are not kind of built on exploring a whole space of functions, and then it seems wasteful to base all our arguments regarding how well an algorithm is going to do in terms of generalization by considering how big the function space it is that it's not exploring. I mean, um, and the proposal that we discussed the last time was that maybe we should consider the properties of the algorithm, like stability, and try to use that to derive generalization bounds or performance bounds more generally for the algorithm. So with this, the analysis is really in 2 steps. It should generalize, and it should also find some good predictor with good empirical loss. If the 2 things happen at the same time, then you have a jackpot, you have a good algorithm. So you're separating these 2 concerns. And just to understand this generalization, maybe you don't need to argue about this, the size of these sets that the algorithm is searching in implicitly. And so one notion that we introduced was this uniform stability notion. And just to recall this notion, if you have an algorithm that takes an n tuple and it returns some response, and it's in the loss space, it returns some response. I'm like, it's of course it returns some weights or whatnot, plug in losses, and then you eventually end up with some loss function. Then you call the algorithm epsilon uniformly stable. If you take any 2 data sets which only differ by 1 data point that is matched, like the ice data point is not the same, but all the other data points are the same. And the algorithms, the laws that the algorithm assigns to the 2 data sets differ only by at most epsilon, then you call the algorithm epsilon uniformly stable. If you have a randomized algorithm, then you basically argue about the expected loss function that the algorithm assigns to any data set. And just a very basic calculation showed that if you have a uniformly stable algorithm, then its test error, which is what we denoted by here, is upper bounded by its empirical error plus the stability coefficient or sensitivity coefficient of the algorithm. So if the algorithm is not stable, then these 2 are the same or very close to each other. And in particular, if this is small, then the whole thing is going to be small as long as this is small. So it's like, this is the separation of these 2 concepts. Okay, great. And then we had a more complicated result that was saying that for the test loss, for the predictor, the expected choice of the randomized algorithm, but you keep it random, the input to the algorithm is random. So over the randomness of this input, you can get a high probability loss that is of the same style as we had before. So there is an empirical component to it. And there is a less empirical component that we discussed where you take an expectation, but fine, okay, like that's the price you pay. There's this alpha here. So this alpha was coming from this this inequality. So if alpha is 1, then this is not there. And then there are some 2 terms. There is a concentration term which just comes usually from the properties of the losses. And there is a concentration term which comes from the stability of the ergatum. And this is like the sub-exponential type. And there is a little penalty that just depends on the stability that's similar to this gap that we had, or like this epsilon penalty that we had before. And we were just proving this theorem. So today we should be putting these results to some good use. And actually what happens is that we don't do it that much, but we're introducing yet another stability concept. Like there is some hint of like how to use this. Okay, this uniform stability is nice because this is what is known to give you these high probability bonds. But there are other notions of stability, like what I'm going to introduce now. This leave-one-out stability notion, for example, which doesn't do that, but it's like maybe it could do it, but no one bothered deriving high probability bonds, or maybe I don't know whether it's possible. But so these high probability bonds do not exist for this type of stability, but in terms of expected bonds, like bonds on the expected performance, with this new notion, you get somewhat better results. So we are going to talk about this. So this leave-one-out stability. So this is what Pong kind of likes. I think that's why we're talking about it. Looks like as follows with our notation. So you have a randomized ergatum. And okay, so we need the ergatum to be defined for two sample sizes, n and n plus 1. So that's kind of unusual. Usually we just like fix n, and then you just like concentrate on like how does this ergatum work, or what you're considering, how does it work for n? You never think about like what happens with n plus 1. But in these proofs, what happens is you take away one sample or you add one sample, and then it's like leave-one-out testing. And then you get something else. So you need to consider a different sample size. And the simplest thing is to just assume that the ergatum is defined for two sample sizes. And the results are going to be considered with a sample size of n. So this is your target sample size. And this is just an auxiliary thing. It doesn't even have to be the real ergatum. It could be anything that you are just cooking up. And then in one example, we will see that we just cook up something that's used for our purposes. But in a lot of applications, and then this is the origin of the whole thing, this would be the same kind of family of ergatums. It's like, let's minimize the empirical risk plus some penalty. And then it doesn't matter what the sample size is, you always do this. Or let's run SGD for this many steps, no matter what the sample size is. Okay. But here you have the freedom of doing something else. Anyway, so we say that like this dually defined ergatum is epsilon leave-one-out stable. So this LU is not that low, but it's the abbreviation to leave one out. With a specific function epsilon that takes an n plus 1 tuple and an extra argument and returns no negative numbers. If the following holds, if you kind of run the ergatum on an n tuple and you're testing it on a new example, this is upper bounded by running the ergatum on the n plus 1 tuple and testing on the last component of the tuple plus an error term. So you can imagine that this is going to do some empirical risk minimization. Then you expect this term to be small. So this kind of is essentially capturing something useful about this, the behavior of this algorithm then, okay? This extra term epsilon. And so if you have this, so you have this K, randomized algorithm, which is this leave one out stable with this epsilon function. And it happens that this part here and this part here. So you could even consider like adding this up. It's like we're gonna get these upper bounds, which is just the sum of mu k with an n plus one tuple and the epsilon. And it's symmetric in the sense that if you are here, you have n plus one arguments, and you are swapping the ice component with the n plus one component, okay, and replacing this zn plus one with the ice component. So let me write this out. How does this look like? So instead of having z1, the normal ordering, so instead of having this, and this is duplicated because here, like the last component is repeated. You swap this guy with this guy, and at the same time, you replace this with this. Oh, I guess I have some typos here. This should be plus one. So so if we just do this, and then we are also replacing Zn plus one with Zi, then we kind of are not doing anything. We just rename the variables. Everything is the same. But now if you replace these guys back, so you're swapping these two guys, again, then what happened is that the very last component here was agreeing with the last component there, but here it's not agreeing with that, but it's agreeing with the ice component. So if the underlying algorithm had the symmetry that the ordering here was okay, so the algorithm was insensitive to swapping the ice component and the n plus one component, then this will be the same as well. Like if you apply the algorithm to it, uk and epsilon. So that's the condition. So the condition is going to say that actually it should say this. So if mu k has the property that you take its n-tuple argument, and in the n-tuple argument you are swapping two of these coordinates. Just the n plus one position can be swapped with any other position. Then the result doesn't change. Then something nice is going to happen, right? Okay, so this is actually that I'm thinking about. This just means that like you have complete symmetry in terms of whatever order you are putting these things, because You can always swap something to the end and then swap it with something else. So if you want to swap two elements in the tuple, which is not the last component, you will first move the first guy to the end, and then you move that to the second position. So you can swap any two elements. So it's like permutation symmetry. Okay. So mu k and epsilon are permutation symmetric. Then what you can do is that you can conclude from the previous inequality and this symmetry assumption that the expected performance on a Q-test sample of the ergotam is going to be upper bounded by its empirical performance on the n+1 tuple plus the empirical error of this error component epsilon. And it just basically it's just based on observation that okay, so you have this notation that you're swapping the i's component with the n+1's component. Then on the one hand, if you are swapping the i's component to the n+1's component and the last component is replaced with zi, then that has the same joint distribution as if you didn't do anything. Because it's like everything is uncorrelated or independent, except that the last guy is repeating the one but last guy. They're coupled together. And so this is true here, and this is also true here. So because of that, if you apply, so these two distributions, the distributions of these two tuples are the same. So if you apply, an arbitrary thing to this data, then you had identical distributions, then the function applied to them is going to result in values which have identical distributions too. So this is identically distributed to this. Okay. And at the same time, we knew that this is upper bounded by this. So that was the assumption. And now this guy is, wait, did we use a symmetry? Oh, okay. Oh, yeah. Okay, we haven't used the symmetry yet, but wait. So yeah, so this upper bound holds by assumption, and these are the same in distribution. So this term and this term are the same in distribution. And now you want to forget about that. You are doing this swapping. And if you have permutation invariance, then you can forget about the swapping. So that's the result, right? So in this result, there is no rotation or swapping. So in the last step, this has the same distribution as, well, so this is symmetry. As without the swapping. And then you can take expectation of both sides and conclude that in expectation, this guy is upper bounded by this guy. And then you can take the average over all i's. I goes from 1 to n+1. And that's how you get this result. So this is the empirical average over all of those things. Okay, Roshan.
So didn't like when we are doing this, we don't have the assumption that the mu k and epsilon are symmetric, right?
This is the assumption.
Yeah. So there's no symmetry. Oh, that's about mu k. And then it's epsilon. Okay, I see. Thanks. I just
Yeah,
understood.
yeah, exactly. So without it,
Mhm.
this result wouldn't hold, and you can
Yeah.
construct examples where.
So what are we trying to prove? Like we are saying that if mu k and epsilon have the symmetry property,
Yeah.
and mu
If
k,
mu k and epsilon has the symmetry property, and then uh, k was epsilon LOO stable,
uh,
then it follows that
okay,
this inequality in the bottom holds. So it's
okay,
basically the expected test error can be upper bounded by
mm,
this error, and this error is like, like this is like the training sample error when you're running the algorithm on one extra
right.
sample. So that's why the symmetry was assumed, and like where we're doing these little extra steps so that we can relate it to back what the algorithm would do on n+1 samples.
Yeah, okay, yeah, so,
Because that's something that the algorithms typically control.
right.
And so it's a very silly little statement, right? Because it's almost like you're assuming something for every line of derivation kind of thing.
But this assumption is still weaker. So earlier we were assuming that epsilon is like a uniform constant, but here
Right,
we are
right, right,
only
right.
assuming that epsilon
Oh
has the
yeah,
symmetry
yeah,
property.
yeah,
So that's
yeah,
like,
yeah.
okay.
I mean, like somehow this also came into the mu k,
Mhm. Right.
whereas earlier we didn't have to deal with that.
Yeah.
But this guy here, you choose it. This is auxiliary in the application. So this is your target. And
Yeah.
when you're choosing this, nothing stops you from symmetrizing if
Right.
something was not symmetric.
Yeah.
So it's
Okay.
like
Mhm.
it's not really necessarily such a big restriction.
Yeah.
Yeah.
Um, so are we assuming this mu k is epsilon LOO stable in this
Yeah, yeah,
approximation?
yeah. It's like
Okay.
it should say in the proposition that assume that this is symmetric and k is epsilon LO stable.
Okay.
Yeah. Further questions? Someone
Nope.
ping? Nope. Okay. Okay. Fine. Yeah. Okay. So now comes the first result that is going to worth something, hopefully, after a lot of preparation. But maybe even before that, let me just motivate things a little bit. So where are we going? We want to go here, for example. So this is support vector machines, SVM. Okay. So it's like the finite dimensional version of SVM. You have a feature map that maps your input space, whatever it is, to RD. And then you have your predictors, and it's a classification problem. So the predictors take the form of FWX is equal to the inner product of W and the feature vector with some weight vector W. Okay, so W here is in RD. So that's how you're making predictions. So it's linear prediction. And it's binary classification when the labels are either plus or minus 1. Okay, and you use the hinge loss. So the hinge loss is this loss here. So this is called the hinge loss. So the hinge loss is okay. It takes basically there is the one-dimensional argument version of it. So when you call fx times y, this is a score. And you want the score to be positive. Okay? So if the label is +1, you want to predict some big number. And if the label was -1, you want to predict a big negative number. Okay? So you multiply the value of the prediction with y, algebraic trick. Then you can just say, oh, I want this to be as high as I can push it. I want a big score. Okay, if I have a big score, then how am I going to classify? I'm going to classify as positive label whenever my prediction is positive, and otherwise it's a negative label. So basically the sign function is going to classify, but here we are kind of the sign function in terms of the score. How does it look like? So there is a score here. So as I said, you want positive scores. Okay, so when do you have errors? You have errors when your score is negative. And so the classic, like the true loss, is the so-called 0, 1 loss. This is R0, 1. This is how it looks like. And we are replacing this loss with the hinge loss. And the hinge loss is just this linear upper bound that has this kink. It goes up to 1. It's kind of an arbitrary steepness. And you try to push down the hinge loss. And the hinge loss is an upper bound on your actual loss. So you're hoping that if you keep an upper bound small, then the actual loss is going to be small as well. And of course, okay, then the next step is that you ask, okay, in terms of this hinge loss, how small my test loss is going to be. If you can show that it's going to be small, then of course the 0, 1 loss is a lower bound for the hinge loss, then you're doing well. Okay? So since you started with an upper bound, it's enough to show that the test error using your upper bound on the true loss is small. So we are trying to do that. Why do we replace the 0, 1 loss? We're replacing it because this way we can make things convex and nice and amenable to optimization. And there are various stories that people tell about these SVMs, building a large margin. So the idea here, intuitively speaking, is also that you are penalizing a little bit just because you had to have a convex upper bound on the 0, 1 loss. You're kind of forced to penalize positive scores. So we are penalizing positive scores. So that means that we don't like scores which are less than equal to 1. We want scores to be bigger than 1. So that's like building a margin. That means that like you want kind of like safe predictions. And also like, okay, so there is some geometric picture. You probably took some elementary machine learning class where it was explained to you that if you're adding a penalty like it's shown here, this 2-norm quadratic penalty, then when you have separable data, so it's like, let's say this is your feature space, right? So this is RD. Like the data is mapped through psi here. And you're going to have, I don't know, positive examples and negative examples somewhere in RD. And so when you have a situation where there is a linear separator, okay, I'm very close to not having a linear separator, but so these linear separators that we are considering go through the origin. So you can choose this linear separator, you can choose this linear separator, you can choose this one. Which one would you choose? You kind of want to choose the one that avoids the data the most, that is still separating the data. So that's the idea of this maximum margin classification. And how do you measure the margin? Well, it's like the distance of the hyperplane, the distance between the hyperplane and any point in the data set. It's the minimum distance should be large. And you can show that setting up the optimization problem, which minimizes the empirical loss with the hinge loss, and adds this penalty, this quadratic penalty, really going to choose the hyperplane which achieves this maximum margin for any positive lambda coefficient. It's kind of cool. If there is a separation. If there is no separation, then the coefficient matters more. Then it's like if you increase this coefficient lambda, then that means that you kind of care less about the data and you care more about that you just want, I don't know, like smoothness in a way, or like we are not trusting the data in a way. Anyways, so what we are shooting for is to say that if you're choosing the ERM solution with the hinge loss and this quadratic penalty, so running basically SVM in the feature space, then you can get a nice bound on the expected test loss of the resulting weight that you're reading out. And then this is what you have here. So this is the ERM solution. So this is supposed to be ERM. You plug that in, and you evaluate it on a loss, and you evaluate it on a new test sample, and you take away the randomness of the data. And this is upper bounded by what you would get if you knew the distribution. Okay, so there is a P missing here. So if you knew the distribution, then maybe you would select something like this. Actually, then you would use lambda equals 0, and that would give you the best separator for the test and the hinge loss. And some extra penalty, and this extra penalty is this guy here, and you can see that, well, it's a 1/n dependence, so it's like goes down pretty fast. Of course, in reality, what happens is that you need to trade off with the lambda, this term, and this term, and then that might turn this into a 1/√10 rate. But that's okay, right? Like if you choose, for example, the minimizer of this, so that's your W, so that further upper bounds this, then you get W star here, and then you can trade off with the lambda the optimal way, and then you get this 1/√10 rate where you get like the norm of this W that gives you the best test loss, combined with this quantity here, where, okay, like this quantity kind of cancels this one, so that's like you can just ignore this. And so there is basically this quantity that is going to stay, that you need to take into account. It's like how big the feature vectors are and how big is the W that's optimizing. That gives you the optimal lambda, and you get this 1/√n rate. with that. And you can show that all the terms here are really necessary. It's like you can't, like, this is up to constant factors. This is the best possible scaling you could have in this situation. And it's adaptive to, okay, so if lambda is optimized, let's say in cross-validation, then you're kind of adapting to how big the competitor is, this W star. Anyways, this is where we want to get to. So we would want to get this bound. So you might ask, okay, but can't we just get the same if we are considering, I don't know, covering numbers? I think you can. It's going to be some work. So for example, the W here lives in an unbounded space. And usually in classification, we say that, well, the magnitude of W doesn't matter. But here, the scale really does matter. So you can't really just say that the magnitude of W doesn't matter. So you can't just consider a sphere. But you can do other things. So it's in particular not too hard to get some bound on how big the ERM W's are going to be, because, well, on the empirical, really they're minimizing the empirical risk, and if you plug in 0, then in the empirical risk, then the maximum error that you get from this term is 1. You don't get any error from there, and so you know that your empirical risk at the optimum, your ERM solution is upper bounded by 1, and then the empirical risk is lower bounded by this. It's like, okay, 1 over square root lambda is an upper bound, and then now you can start to play with covering numbers. If you remember, like, the radius shows up in the log factor. It's like, okay, so I think that the covering number bounds are going to give you something very similar to this, maybe some log factors worse. But it's kind of interesting as well that, okay, you can get just bounds using stability for these situations. And then in other cases, maybe the loss function is not bounded. So we were in this argument that I was sketching using that the loss function is bounded. So if that was not the case, like, for example, for plugging in 0 gives you, I don't know, like the responses are arbitrarily big or something like that, no a priori upper bound exists on this, then this kind of fails, and like it can be sensitive to various things. Anyways, this is where we're going. Is it clear? Good. Yeah.
So here we're trying to get this oracle-like inequality, but
Yeah.
like so far we haven't.
Absolutely not.
Okay.
Yeah. Yeah. So it's going to be exciting to get Oracle. I was kind of just alluding to that. Like in this proposition, we have this part, and then this is like an ERM solution. And so from there, you like, you know how to get an Oracle inequality if this was really an ERM solution. And in this application, we actually run ERM. So it's like that is trivial. Yes, right.
Maybe this is irrelevant, but I didn't follow how the covering number argument work.
So in the covering number argument, you need to cover some space. What are you going to cover? You need two things. Usually you cover a ball, and then you argue with some Lipschitz-ness that you don't have to inflate the covering numbers by much. So the Lipschitz-ness does hold here because you have hinge loss. So that's like the derivative of it is at most 1. You have the quadratic penalty, and so the quadratic penalty is like a little bit more inconvenient, but its gradient is going to be bounded as long as you're bounded. So there is something going on with that, but the main issue that you have is that the W space is not bounded. But then you start to argue that, well, it doesn't really matter, because if I would run the algorithm by constraining W to a ball of large enough radius, it would give me the same result, no matter what the data is. So effectively, the W space that the algorithm is working is bounded. It's because of this penalty that it has. So intuitively, you have the quadratic penalty, and that makes it so as if the algorithm was run on a ball of radius 1 over square root lambda, or like square root 2 over
I
lambda,
see.
or something like that.
Oh, it's the dual thing, right?
No, it's not really a dual thing. It's more like, I think I do have written this up, maybe not for this example, but where is this? It's actually for here. Yeah. So even here, like, we are going to need to argue with that the losses are smooth, and so the gradient, we need to worry about whether the gradient is bounded. And so what you do is that you take the RM solution. The empirical loss on the RM solution is upper bounded by, if you just arbitrarily plug in some value there, and you happen to plug in 0. And if you happen to plug in 0, then the hinge loss takes at most 1 for all these samples. So the average of that is at most 1. And the penalty takes a value of 0. So this is actually, okay, not equal to, but like you can be lucky, less than equal to 1. And it's also true that your empirical loss can be lower bounded by just the penalty term, because the hinge loss is non-negative. Okay, and now you just rearrange, and then you find that the algorithm runs as if it was effectively run on this set. Yeah.
Okay, understand.
Yeah, and then from there you can run covering, or you can do the stability analysis. Even for the stability analysis, we need to use this. Yes.
So is the idea that the stability analysis, like, we could have done all of this special case reasoning for this problem, but the stability analysis is going to give us the same result, but in sort of a more general way?
Oh, I mean, like from here, you didn't get anything yet. You were just getting that. So one part of the idea is that if you're adding a penalty, then effectively you're making the algorithm run in a bounded region of the weight space.
Right.
So that's just one part. But the other part is, okay, then you have to do something to get some generalization bound.
Yeah.
That you can fork. You either run your covering argument,
Uh-huh.
or you are running a stability argument.
And for the covering argument, you would need to argue based on the specifics of the problem that you can cover like a small ball, right?
Yeah, and so this would be the ball, and then, okay, how big is that? Right?
But for the stability argument, you don't need to do that.
In the stability argument, we need something. So this theorem, okay, so we are getting to a theorem. So in this theorem, so we have this more generic setting that you have a parametric class of losses, and then a parameters live in a d-dimensional space. So we really like tuned to this SVM setting, let's say. And you are in a closed convex set. And so if it was unbounded, then you can take an unbounded closed set, that's all fine. But it also has to happen that the loss maps are pointwise Lipschitz. And so now, okay, if you take the hinge loss, okay, so this is our loss. So hinge loss applied to FW, XY, blah, blah, blah. You take the gradient or the derivative with respect to W, what do you get? Well, you get the gradient of the hinge. It's 0 or 1. Okay, don't worry about the kink. And from inside, from the derivative FW, psi comes out. Okay, that's okay. That's all good. Like this can be bounded if psi would be bounded. Now this guy here, if you take the derivative, it's just a linear function. It grows with W, so these will not be bounded. It will only be bounded if W lives in a bounded subset. So it's like because of the quadratic penalty, this is this wouldn't work unless you add this additional observation that okay, like this is not a big deal. And by the way, this is the price for that is this, right? Like there's this and then somehow this, and then they kind of add up. Yeah.
Yeah, so I guess so even you won't even get stability unless you argue that that thing is bounded is basically the point, right?
Yeah. Right. Yeah. Not with these tools. Yes.
Right.
Yeah, because here the argument is based on this Lipschitz-Ness, which would be a global property, which is not good. Oh, let me fix a mistake. All right, so let's read this theorem. So we have these parametric losses. W is an element of C. C is closed convex. And we assume that these maps from the parameters to the losses evaluated at some point are Lipschitz with respect to, like here, the 2 norm is used in input space. And from now on, I will drop the 2. And in the output, it's just real values, so it's just absolute value. So this is Lipschitz. And for some future applications, it will be good to add some additional regularization. Fine, we do that. So we consider the ERM for that. And in particular, we are going to make another assumption. And this assumption is going to be that this map is lambda strongly convex. Okay, so this is my abbreviation for strongly convex. So how many people here do not know what strongly convex is? You can write in chat or like just, let's see. Okay, that's pretty good. So strongly convex, just with words, means that it's a convex function and it remains convex if you're subtracting a constant multiple of the squared 2 norm from the function. That's the most beautiful definition of it, and it has some corollaries. So it means also that you can lower bound the function by considering sort of like a Taylor first order expansion and a quadratic term that has this strong convexity constant in it. So the second order term is basically like the number there that would come from the function can be replaced by this lambda. That's it. That's a corollary. It's actually equivalent to the other definition. But the first definition is nice because it makes it sometimes super easy to verify whether a function is strongly convex. So for example, with the SVM example, so we added this quadratic penalty term. So if you subtract it, okay, the penalty is not there. The remaining one is it convex? Well, yeah, you plug in a linear function into a convex function, therefore it's going to be convex. So that it's super easy to verify strong convexity. Okay, so you do this, and then you consider two algorithms. So here is an example where we are kind of making up of how the algorithm behaves on the n+1 tuple. So the n tuple, we just take the empirical mean. So this is, recall, this is just empirical mean at samples z1 to zn. And you take the empirical mean and you're minimizing that over C with respect to this extra regularized function. And I just wrote it out like this is how it looks like. And for the, because we're going to use this leave one out stability, we need to specify what the algorithm is going to do with n+1 samples. And with n+1 samples, it kind of does the same as before, except that it's like kind of the penalty here like would be age, but here we are just taking a slightly smaller penalty n over n+1. It's just for algebraic reasons, like in the calculations, this is going to be a little bit helpful. Sometimes you do these things. In the applications that, so for example, when you apply it to SVM, age is 0. So it's like kind of doing this for nothing. But there could be some applications where this is also useful. Okay, and then there are a few statements that you can make. So the first is that this map, this A map, is this epsilon stable where, I guess, to be clear, so the n tuple is not even used, and here this should be capital G, I think. So this G squared, so this was the Lipschitz constant here. That's your squaring divided by lambda times n+1, and so this is the LU stability. It also follows with the same argument that this A itself, just with this part, is uniformly stable as long as you have a uniform upper bound on the Lipschitz constant. That's usually how it goes. So this refined LU stability allows you to have Lipschitz constant that change is the example. So it's like a more refined notion. And finally, if you take a sample of size n from a distribution P, then and you run the algorithm on this sample size, you get this weight. Then the test error of the weight is upper bounded by the smallest possible error that you would get if you knew the distribution plus a penalty, and the penalty just depends on the stability coefficient, so it's kind of neat. It's not really surprising given the previous proposition, right? Because I was already arguing that it's like it already has this form that, like, if the algorithm run on n+1 samples, well, it's going to do at least as well as this. Okay. Okay, so to prove this, so the interesting part of the proof is really how do we get this stability going for these algorithms? And for this, we need to have some basic results about convex functions and optimization with them. And these are just like the simplest results that you can imagine. So the first order optimality conditions for convex optimization. So you have a convex function f defined over this closed convex non-empty region. And you take a minimum of this, and then there are two parts of the statement. The first part says that no matter how you take a minimum and take an arbitrary point in the domain, and the first part states that no matter how you took this other point, there is a subgradient of the function at x star. So we're assuming that this x star is such that the subgradient is non-empty. In the applications, this is not a problem, but there's some nasty functions when this may not happen. Although I think that if this is a minimum, maybe it always happens. Anyways, so that this inner product is not negative. Okay, so that's the first part. And the second part says that if f is strongly convex, lambda strongly convex, and you also find another subderivative such that this inequality holds, then you can conclude that x is not too far from the optimum. Okay, so this inequality kind of says that if you're going from x towards x star, it's like if this g was a small number, if it was 0, then this would also be an optimum, right? Like, and if g is a small number, then it's like you cannot go too much. Like you cannot increase the value, like intuitively from going from x to x star, you will not be able to increase the value too much. And therefore, x should be also near optima. So it should be close to x star. So that's kind of the logic of it. But you will see the proof. So the first part of the proof is, okay, basically I ignore it, but just noting that if you take a directional derivative of the function in the direction of x minus x star, then it will be equal to the inner product between some subgradient and x minus x star. It's like just definitions, just using the definitions. It's actually, this is you can be more particular. This will be the subgradient that maximizes this inner product, actually. Anyways, so once you have this, it's like super simple, right? Because you have this, like imagine that the function was just one-dimensional and it's defined on the line between x and x star. So it's like a little figure. So let's say this is x star. This is your x. And the directional derivative, so we just found, okay, so this is supposedly an optimum. This is some point in the domain. So then the function must be not decreasing when you're going from x to x star. So that means that the directional derivative of the function, if you evaluate it at x star, should be non-negative, right? So it has to be an increasing function. So that's it. Like it's like one-dimensional optimization. Basically, it does it. If it was negative, then okay, you could find in the neighborhood a small point, and then like that goes in, like stay inside the constraint set, and where the function value is smaller than the function value of a star. But it's like okay, some details. But it's I think that the essence is just like one-dimensional. It's clear, and this is just directional derivatives. Okay, second part, that's just a little algebra. So it has two parts to it. So first, so strong convexity definition tells you that the function can be lower bounded by its linear approximation plus a quadratic term. Okay, so we have this linear approximation quadratic term. So do this lower bound for x star. So we are taking basically the Taylor series expansion at x. Okay, so this theta tilde is a subgradient at x. And we have this, we assume that this relationship holds. So we can further lower bound this by this quantity. Okay, so now you flip things around. By strong convexity, the analog relationship holds when you're upper bounding the function value at x. But now base everything on x star, so now you got a theta there. And just notice that this is non-negative because x star was an optimizer, right? So part one gives you that that's non-negative, so you can drop that. You get something greater than equal. So you add the two inequalities, and notice that, well, this is going to cancel this is going to cancel that. All right, okay, this cancels this, and this cancels that. So you end the the end inequalities, and then move this to the other side. These two guys are the same. You get this inequality, reorder, you got the result. So it's really just working with definition of strong convexity. Yes, try.
So where did we use the assumption that it is convex and closed?
I think that x star exists.
Okay. Also, are we assuming f is
Okay, so the
differentiable?
convexity is no. Convexity is used here. The convexity of the domain, because in actuality the argument goes like this: you have this C, you have your x star somewhere. There is this other x, and the subgradient or the gradient lies like that, and so you take the negative of it, and it points inside. And from that it points inside, you conclude that you can actually find points. Well, okay, so you need that this little segment lies inside the set, so that's convexity. So that's where the convexity of C is used.
Okay.
Okay.
Where is the closeness used?
A closeness is just used that this argument is well defined.
Okay.
Like if you don't have closeness, then of course that's what are you talking about? If you would just say that, okay, let's assume that argument exists, I don't think closeness is used anywhere.
Oh, I see.
So if you would start saying that let f be a function defined over this domain, C, which is convex and non-empty, and x star is a minimizer of f over this domain, then you get the same result.
Okay, this is the projection theorem, right?
You don't really need a projection theorem. You just like assume that the minimizer, like it becomes an assumption of this, the statement that the minimizer exists.
Okay.
Or you state the result for any minimizer, and so if it doesn't exist, then it's like a vacuous result. You don't care.
Okay. Also, like, do we assume this f to be differentiable?
No. These are sub-differential. So the hinge is going to ruin everything, right? It's not differentiable.
So I didn't quite follow the proof of part one, like f prime. If it doesn't exist, I don't.
The directional derivatives always exist.
Oh, I see. This is directional derivative.
Yeah. So the directional derivatives exist no matter what. Think about the hinge. It's like, okay, if you are the king, then left derivative, yes, it exists. Right derivative, yes, it exists. The convex functions do have this funny property that the directional derivatives exist.
For convex functions.
Yeah.
Okay.
Okay. Right. This is a crash course on convexity as well. Okay. So let's prove this thing. Part one. This is Levin-Out stability. We're going to take this n+1 tuple, define empirical loss for the n tuple, empirical loss for the n+1 tuple. Okay, this is actually not the empirical loss, but it's like discounting this guy, right? Like it's just instead of one coefficient, you have an n over n+1 coefficient carefully crafted. And let Wn be what the algorithm gives you as the sample size n, and Wn+1 sample size n+1. Okay, and they happen to be the minimizers of these losses by definition. This is how we defined the algorithms. And okay, for this proof, for simplicity, I assume that Ln is differentiable. If it's not differentiable, it's a little bit more complicated to say that, okay, like which sub-differential you're using, but it's nothing. You can think through it. So let's say it's differentiable, then you can just take the derivative of Ln at Wn, and this first order optimality lemma, so the previous lemma, gives you that, okay, this inequality holds, right? So gradient times the difference, where you're taking the difference between your point where you're optimizing and any other point, is non-negative. So I'm going to call this star. So now this the loss function that corresponds to sample size n+1, this is basically the loss function that the empirical loss that you're getting, which is penalized with this age, discounted a little bit, right? Because here you have a 1 over n coefficient, so you multiply with n, divide by n+1. So the part of the loss which corresponds to the data, it has the correct coefficients of 1 over n+1. You're missing the last term of the loss. You add that, and you're done. And this is exactly so to why you have here n over n+1 age. Because here you had 1 over n age, so you multiply with n over n+1. Okay, you get n over n+1 age. Okay, so this is just algebra. After that, you can take the gradients of both sides. Okay, this is where I wanted to avoid writing things like, oh, the set of subgradients is such and such, right? Like you have to know a little bit about subdifferential calculus to know what exactly to write here. And okay, so this what the gradients are satisfying. And now, so let's take a look at the gradient at the function that corresponds to sample size of n+1. So this was gradient a sample size of Ln at Wn, and the only difference is that here you have n+1. Okay, but otherwise this is kind of the same inequality as this. And in fact, like here we know that this is non-negative, but here this is n+1. But we calculated that this is the same as this plus this. So this guy goes there. That gives you a non-negative value, so you can drop that. What remains is this times this. Okay, so that's the lower bound. So by star, this is lower bounded by 1 over n+1, gradient of G, Wn, Zn+1 times Wn+1 minus Wn. Okay. So now you can apply Cauchy-Schwarz. So you take this, you take its norm and take the norm of this, the negative of the product of these two norms is a lower bound on this inner product. Okay, that's just Cauchy-Schwarz. And then the norm of the gradient of W is upper bounded by the Lipschitz constant, right? So if a function is differentiable and it's Lipschitz, then the Lipschitz constant upper bounds the derivatives. So that's where we get this g of zn plus 1. Okay, because this function was at z is gz Lipschitz. And we got the negative sign n plus 1, and then just the norm difference between the weight vectors. And so now we are going to apply the first order optimality to Wn plus 1 with part 2 of the lemma. So part 2 of the lemma was ensuring us that if you have an optimizer, and that's going to be our Wn plus 1, and this is going to be Wn, and you take a gradient at that optimizer, and this is lower bounded by a negative value times the distance between the two vectors, then the distance between the two vectors cannot be too large. It's going to be upper bounded by whatever you see here over lambda. So just apply that. So here, oops, we have this inequality that allows us to use this part 2 of the lemma. In particular, this is going to be this constant g in the lemma. So, and Wn plus 1, this guy here, was an optimizer of this. So that's why we can apply the lemma. And so from the lemma, we're going to conclude that the distance between these two guys is upper bounded by this divided by strong convexity, that's lambda. So we get this inequality. Good. And so finally, if you evaluate the loss at Wn, look at Zn plus 1, and you compare it, like you subtract from that the loss evaluated at Wn plus 1 at Zn plus 1, then Lipschitzness tells you that this is upper bounded by this. So that's just Lipschitzness. And we have upper bounded this guy with this, so plug that in, so you get this. And this is exactly saying that A is g squared over lambda n plus 1, leave one out stable. Okay, so uniform stability goes the same way. You have to have both sides of the inequality, but other than that, it's the same thing. And you can have that. And you take supreme. So now, okay, notice that this ergotam and the epsilon is symmetric to these swaps or permutation of the sample, because it was just a minimum, so it doesn't care about the order. So that's a good. So in the epsilon, there is absolutely no dependence on the top. It's just like some extra input. And so the theorem then gives you that the expected test loss is upper bounded by the empirical loss plus the empirical stability values. And so the empirical stability values, what are they? So this G just depends on Zn plus 1. And you can rotate that around. It's like this Pn plus 1 is just plugging in Z1 to Zn plus 1, take the average. They have the same distribution of Z1, So the empirical mean doesn't do anything there. It's just taking Z1, same as taking Z1. And then, so it was G squared over lambda n plus 1. You copy that here, evaluated at Z1. Expectation was there, copy it over. So that's that term. And here we just noticed that this is exactly the loss in ln plus 1. Okay, no, it's upper bounded by the loss, because in the loss you have age, and here you don't have age. In G, you don't have age, but here you are adding an age, and n over n plus 1 age. So that's why you have this upper bound, and then you add an extra 1 over n plus 1 there, so that you can have all the losses. So the empirical loss plus h times hw. Okay, and here I was also swapping out the random w. The random w is optimizing this empirical loss, so I can swap out any fixed value of w to get something larger than equal, right? So I just take any w, so I get an upper bound there. And so no, notice that if you apply the expectation to this, then you get this quantity here. It's just like the true mean, or the test loss at w plus hw. Finally, note that w was arbitrary. You can take the one that minimizes the left-hand side, and the inequality stays true. So that's the argument, and I ran out of time. Too bad. So here we are almost discussed all this proof is the hinge loss and the linear stuff, and like just like one step remains. So verifying the conditions of this theorem. So let me do that very, very quickly. So what are the conditions? So if you want to apply to hinge loss thing, so this C we discussed how we get it. It's like the radius of ball of radius square root 2 over lambda. The Lipschitzness, we get it because we are over the this ball, and the maximum is the ball. So this is the radius of the ball. So the maximum norm that you can get is square root 2 over lambda. It will be multiplied by lambda. So it's like square root 2 lambda. Okay. So from here, you get square root 2 lambda. The maximum value that you can get here is 1. Here you get the 2 norm of the psi. Okay. So that's your G. Okay, that's the proof. And lambda strong convexity we already discussed, right? Like it's like by construction it's lambda strongly convex. So the conclusion is that you have this inequality. So now you just have to imagine that there is psi here and square root 2 lambda. And other than that, just plug in what we had here. Okay, that's the result. And I didn't have time to cover so many beautiful other things. So I don't know, I'm just too slow. Even though I'm just pointing at the screen. Yeah, so there is another result that whose proof I didn't even want to present to you. You just had an extra condition, which is that these losses are also smooth. So that means that the derivative of the loss with respect to W is L Lipschitz. And if that happens to be true, then you can show that you just take the A is just the empirical risk minimizer, and A on n plus 1 is empirical risk minimizer. Then A is epsilon LO stable, where you have to plug in So this is like the kind of a smoothness thing. So the gradient of the loss, whatever the empirical risk minimizer gives you is n plus 1 samples and evaluated at this new sample. And of course, this is again symmetric, so all is fine. And you can get this upper bound, and if you get this upper bound, then sometimes that's a little bit better than the other upper bound. So I'm not going to take more of your time, but it's like the example is just squared loss, squared loss and linear prediction. And you can get an upper bound like this. So it's like sigma squared is kind of a variance term, and like it's like the smallest error you can get, and then there is some penalty, and yeah. It is not super satisfactory, if you ask me, this result, because if you optimize the lambda, you get a 1 over root n result, and like, that's not the right rate.
Yeah, it should be faster.
That's not the right rate for square loss, but fine, okay. This is what stability gives you. That's it. At least it gives you something. I guess you can blow up the class so that this is the optimal rate. And maybe stability is still going to give you the same rate if you're lucky. I don't actually know. But that would be one idea.
So this was just using smoothness, but not using any strong convexity, because
It does. No,
Oh.
no. It does actually use. It's like you're penalizing with lambda. So there is this lambda.
Right.
Yeah. It's like, yeah, square loss and lambda penalty. Yeah. And then for smoothness, you calculate the second derivative, and then you find that, okay, you need to upper bound this. Yeah, and that's where this is coming from. Yeah. Okay. And then I had something about SGD, but never mind. It's just not enough time. Maybe next time. Okay. Oh, almost there. Although I wanted to finish this chapter this week. By the way, next week on Tuesday, I'm just going to post some notes. There's not going to be a class because I'll be traveling. This is one travel that was scheduled. So I post some notes and you should read it. And then the next class, we're going to discuss it. And then we'll try to move forward.
You're going to miss 2 weeks of climbing?
Yeah, in Montreal. I'm visiting Montreal. So it's I don't think that there's going to be climbing, but I hope that I'm staying for the weekend. So if you want to climb, then I'm open.
I do.
Okay. All right. Okay.
Alex, you just need to fly over.
Yeah, I don't think we have the funding for that.